Welcome to my new calculus channel. Today I'll be discussing Euler. So the topic today is Euler, and I'll be discussing a few of his ideas regarding algebra, fractions, infinite series, and the like. So Euler was not a bad mathematician, but he made some really serious mistakes, and I'm going to be showing you a little about how Euler thought in this, or Euler thought in this video. I'm going to be calling him Euler because most people don't really know how to pronounce that name, and it doesn't matter whether I say Euler as they say it in German or Euler as they say it in English. So Euler began his Elements of Algebra. Let me just write that down, because I'll be referring to the document Elements of Algebra, which, by the way, is a very good book to read. And I'd say that it's not as good as Euclid's Elements, but I'd imagine that anybody who wants to be called erudite today, or at least even be called a mathematician, can't claim to be a mathematician unless he's actually studied the elements of algebra by Euler. There's no way you can claim to know mathematics without having done a study of this book by Euler. Of course, to be an exceptional mathematician, you'd need to have studied the works of Archimedes, and obviously the Elements by Euclid comes first. So I would say Elements by Euclid, then the Elements of Algebra, and then the works of Archimedes, which are not that easy to understand and require a lot of study. So anyway, let's look at, I've written some page numbers here which I'd like to focus on. Let's go immediately to Euler's document. So Euler had a reasonably good idea about fractions, but he really didn't understand fractions that well. Okay, so, and that's part of the reason that modern academia don't really understand fractions too well either. So we'll see as we move along here what Euler thought of fractions. So he says, for example, that in 76, the nature of fractions is frequently considered in another way, which may throw additional light on the subject. If, for example, we consider the fraction 3/4, it is evident that it is 3 times greater than a quarter. That just shows to me that Euler didn't really quite know what is a fraction. I'll explain more in a minute. Now, this fraction, a quarter, means that if we divide one into 4 equal parts, this will be the value of one of those parts. Well, it is obvious then that by taking 3 of those parts, we shall have the fraction 3/4. Okay, what Euler didn't understand here, and what most academics today don't understand, is that when we write a fraction such as 3/4, no division is taking place. It has already taken place. Do you understand that? So Euler said something which indicated he might understand. He said, take 1/4 and 3 of those, right? Yes, that's closer to the original understanding. In other words, it's saying divide the unit, which is 1, into 4 equal parts, and then take 3 times that amount to get 3/4. That is more the correct understanding. So he seemed to have been able to see it from all ways, but somehow just continued to refer to this as 3 divided by 4, which is actually wrong. It's not 3 divided by 4. This is a completed process. Nothing remains to be done here. There's nothing outstanding here. When we write 3/4, it means the number 3/4. There's nothing left to do. Okay? So the problem with Euler is that he never actually settle down dogmatically to state that this means 3 of 4 equal parts, because when you have a fraction, this part here, let's take a fraction a over b. This part here tells us how many equal parts the unit has been divided into, okay? Equal parts of the unit. So in the case of 3/4, the unit, let's say, is divided into 4 equal parts. These parts are all equal. And 3/4 of that is simply this, yes? Okay. So that is really the meaning of a over b. It doesn't mean that a has to be divided by b. The division is complete. There's nothing pending. Right. So let's just erase that so we can carry on. I need some space here. And that, and that. And let's carry on looking at this document here that he wrote, the book that he wrote. So he says, in the same manner we may consider every other fraction. For example, 7/12. If we divide 12, if we divide unity, you see that? If we divide unity into 12 equal parts, that means the unit, or 1, then 7 of those equal parts will be equal to this fraction here, which is 7/12. So it seems like from that particular paragraph, Euler understood what is a fraction. But it doesn't take long before we start running into problems. So let's continue down in the book and see what conclusions Euler began to reach. So, okay. So he says in this he starts off actually in 80. It says, it is true to divide the length of a foot into 1,000 parts, then those parts will not easily fall under the cognizance of our senses. Oh, that sounds very much like some academics I know today, where they talk about about numbers needing to be stored, or not enough storage space, or not having enough resources to represent a number, but view them through a good microscope, and each of them will appear large enough to be still subdivided into 100 parts or more. So it seems in this particular case here that you have some kind of mental block with respect to representing numbers. We don't have to see those parts under a microscope. In fact, the microscope, it has nothing to do with mathematics, just like physics has nothing to do with mathematics. Mathematics is not governed by the laws of physics. So we don't need to necessarily see those 1,000 equal parts, but to imagine that they are possible. So it says, at present, however, we have nothing to do with what depends on ourselves, or with what we are really capable of performing, and what our eyes can perceive. The question is rather what is possible in itself, and in this sense it is certain that however great we suppose the denominator, the fraction will never entirely vanish or become equal to 0. Now notice that it says the fraction will never entirely vanish or become equal to 0. And then we move on later on to 82. So it says, to express this idea according to the sense of it above mentioned, we make use of the sign infinity, which consequently indicates a number infinitely good. Well, that's Euler's first mistake. No number is infinitely good, and that sign there doesn't denote a number. And here's the first big mistake, and we may therefore say that this fraction, 1 divided by this symbol here, is in reality nothing, because a fraction cannot be reduced to nothing until the denominator has been reduced to infinity. Well, this flies in the face of what he said earlier on. If the denominator is the number of equal parts of unity, Euler is saying here that you can actually divide the denominator into infinitely many equal parts. Okay? Infinitely many equal parts. That is such rubbish. Okay? That is rubbish. You cannot divide the numerator and call it. You cannot even use this symbol in a fraction. You cannot use this symbol anywhere in this fraction, not on the top and not on the bottom, because this here means that b has been divided into equal parts of the unit, into b equal parts of the unit, and a enumerates how many of those parts we have. That's why it's called the numerator. And b the denominator, because it tells us about the denominations. Yes? Okay. So Euler seems to forget what he just said, and then he says in this paragraph, we may here deduce from it a few consequences that are extremely curious and worthy of attention. The fraction, big mistake, 1 over infinity is not a fraction. Represents the quotient resulting from the division of the dividend 1 by the divisor, this symbol. So as you can see, that's absolute nonsense, but Euler began to think that way. Yes? And now we know that if we divide the dividend 1 by the quotient, which is equal to nothing, we again obtain the divisor. So he says ultimately that the division which arises of 1 by 0 expresses an infinitely great number. And finally, we reach the climax of all these ideas in paragraph 84, which says, this opinion is inconsistent with the just principles which you have laid down, for 1 divided by 0 signifying a number infinitely great, and 2 divided by 0 being the double of 1 divided by 0. It is evident that a number, though infinitely great, may still be twice, thrice, or any number of times greater. So what does that remind you of? The idiot, the father of all mathematical cranks, George Cantor, because this is probably where Cantor got some of his moronic ideas from. So, and then he says there appears to be a fallacy in this reason. No, it doesn't appear to be a fallacy. There is a fallacy in that reason. And of course, Euler tries to show that 1 divided by 0 is equal to this, or by a series of numbers increasing in any given ratio. Okay, now let's just look at that, the representation of 1 divided by 0. So Euler recognized that you can actually express a divided by b plus c in closed form using several number of terms by just doing the long division, right? So that's not hard to see. Just say a divided by b plus c, and then b goes into a over b, and that will give us a plus ac over b, and it will be ac over b, and then obviously if we divide this again by b, we'll have minus ac over b squared, and that will give us minus ac over b, and minus ac squared over b squared, and that would be ac squared over b squared, and so on, right? So we'll have over here ac squared over b cubed. So we get this series, as you see over here. That's for a over b plus c, and obviously many of you know that this series here will be equal to 1 plus x squared plus x cubed. And if we take the, for example, over here, if we stop here at this particular point, right? Well, actually, I'd like to stop a little bit sooner, but let's go on here. So let's say that we've done this here. We've taken this particular part and we multiplied out, and that would be ac squared over b squared plus ac cubed over b cubed. So we'll have this whole thing here, right? This whole expression here, minus a, actually I want to simplify this. Let me simplify this a bit. I don't even want to go this far. So let me just take this out here. Yeah, okay. So get rid of that. I don't have space to do a whole lot, so I'm not going to do it right now. No, I don't need to do it. So anyway, that goes, b goes into this amount, and then we multiply that, and we get that, okay? And then we left it ac squared over b squared. So this here is actually equal to A over B minus AC over B squared and plus AC squared over B squared B plus C, right? That's the closed form of A divided. In other words, this here, okay, is what A over B plus C is equal to, right? So not to go too far, we can also express this here in the same way, closed form. But Euler just does something really stupid. He just tosses away the rest of the terms and, you know, follows the approach of Newton, where Newton just decided, I don't really care about the entire infinite series, you know, so I'm just going to toss away these terms and just look at the first few. Now, going back to this particular question here, where it says 1 divided by 0 is equal to 1 over 1, it is a fallacy, because if you put that in there, you're going to get 1 plus 1 plus 1 plus 1. So this here has no sum. Okay, there is no way to sum this. And what happens if you try to look at this in closed form? Can you think about what happens when you look at this in closed form? What answer are you going to get? Well, let's do this slowly. Let's look at the result of 1 over 1 minus x in closed form, right? So let's get a fraction for this in closed form and see what happens. So this is 1 minus x, and that's x, and that's going to be plus x, and that's going to be x minus x squared. Okay, so we can write 1 over 1 minus x as 1 plus x plus x squared over 1 minus x. Okay, so this is the closed form. This is the closed form, right over here. What happens if we put 1 inside x here? Well, we're going to have 2 plus 1 over 1 minus 1, which is nonsense, right? So it's not possible to do this at any time or given any of the many closed forms that one can have for this expression. In other words, 1 over 0 is meaningless nonsense. It's not undefined, it's meaningless nonsense. The unit cannot be divided into 0 equal parts. It just doesn't make sense. So Euler starts off right, and then he ends up just going into many different conclusions that are wrong, plain wrong. So, okay, so we've looked at 59, page 59. Let's see what Euler does on the following pages. Okay, that I've looked at, that I've marked. So if we go to page 129. Okay, 129, and all of them need to start with, okay, 129. Alright, so this is where he actually starts describing how to obtain the series. And then he says something really stupid here. He says let A equal to 1 over 3, which is a third, and our fraction A, 1 over minus A, will then be that particular expression, which gives us 3 halves, which is 1 1/2, which reduced to the infinite series becomes that, which is consequently equal to, no, it's not equal to that. Okay, so this infinite series was the first time that Euler started taking the approach that S is equal to Lim S, yes? Which is obviously wrong. I mean, when we write a third plus a 9 plus 1/27 plus, that is a series. That is what S is equal to. The limit of, is that what, isn't that what he wrote here? Let's just double check on that. So 1, 3, yeah. So now we need to find the limit of that, right? Okay. So the limit of this is given by the formula 1/3 over 1 minus a third, right? Which is a third over 2/3, which is a half. Right? So the limit of this series is a half. So Euler is saying that that whole thing was equal to half, which is absolute rubbish, because this here is an indeterminable, let me write that properly, indeterminable sum. Okay. We can say nothing about this actual sum. Yeah, we can talk about the limit, which is a half. What that means is if we add many terms here, as many as we like, we'll never get to the half. And if we consider S in its closed form, it will never equal to a half. Okay, so you can go back and look at the closed form and see for yourself that no matter what closed form you have, you'll never get a half. Yes? Okay. So that is where Euler begins to go off the track in a big way, and that is where modern academics have also gone off the track. So as you see here, he shows how you can do this division by using partial divisors. So this is something he learned from Newton. Newton did a lot of this in his famous work, the Analysis, and he also used this in finding the sine series as well as the inverse sine series and so on. Okay, so let's go back to this particular slide here, and let's see what happens. We have 129. We've dealt with that. Let's go to 207. 207, and on 207 we'll see that Euler continues with this and reaches the same conclusion again, that this series here is equal to 10. And watch what he says here. He says which series is expressed by a decimal fraction. Right, did he say that the series there is equal to 10? No, he says it is expressed by the decimal fraction. He didn't even add ... at the end of his. So modern academics will now say 9.999 ... is equal to 10, right? Yeah. Euler said it's just expressed by that. Why express it by that when it can be expressed with 10? So obviously Euler was just experimenting here. He didn't really know what the correct answer was, or the correct solution, and how to resolve all these issues in a logical way. And that's probably because Euler just simply accepted the conclusions of previous mathematicians as being correct. In fact, Euler even noticed that Newton was not using the closed form. So, when Newton did things like A over B plus C and do the long division, the so-called long division, it's not long division. When he did that, Euler just assumed that that is correct, but Euler did notice that this here can be written in infinitely many closed forms, which always give the correct answer. Okay, so if you write this in a closed form, it will give the correct answer. But if you just decide to throw away the rest of the terms, like Newton did, well, then you're going to have problems, because there is really no such thing as an infinite series, and infinity is itself an ill-formed concept. Cannot be reified. It's a junk concept. So let's get back to this document again and see what we have here. Euler continues on to show here that the decimal fraction whose value is a third cannot strictly ever be discontinued. So he says it cannot ever be discontinued, but that it goes on ad infinitum, repeating always the number 3, which agrees with what has already been shown, namely that the fractions are equal to 1/3. Well, they're never equal to 1/3, and there is no such thing as ad infinitum, because that is junk. You cannot reify, or construct, or have an instantiation of ad infinitum. It's just not possible. Okay, so that was page 208 and 209. I don't think there's time to go to 506. That's Euler's ideas on continued fractions. I'm a little tired right now. Maybe I'll save that for another video. But there you have it. Those are Euler's ideas, and where we got this wrong concept of S equal to Lim S. Very, very, very bad idea. So, this is the New Calculus channel, and I'm John Gabriel. Till next time, goodbye.